Hi everyone, my name's Rizwan. I'm from Google DeepMind, and I'm also one of the organizers of the MenaML. So up next, we've got Badih. He's a research scientist from Google Research, giving a talk on privacy considerations and mitigations in Gen AI.
Yeah, thank you. So I guess we can start. So today LLMs are mostly trained on public data. And nevertheless, part of the public data contains some sensitive user information. So going forward, as we're running out of public data, there is increased tendency to train on some sensitive user data in order to unlock higher utility for the LLMs. User data can also be used at inference time in some agentic applications. And all of this, for it to be possible, it has to be done in a careful way so as not to compromise user privacy. So in this talk, I'll be giving an overview of some privacy considerations that arise in generative models and agents. I will survey some mitigations that have been researched and implemented, and I will discuss some open research questions in the area. Okay, so let's start first with some concerns that arise when training language models. So the first one is about input reconstruction attacks. So you could take an off-the-shelf LLM like GPT or Claude or Gemini, and it has been observed that if you prompt it carefully, you can get it to output some potentially sensitive user information. So the attack that I have here on the slide is from a couple of years ago, and it's a very simple attack. So they found a very simple prompt. And if you use that prompt, you can get some sensitive input information that is returned by the LLM. In this case, the prompt was just repeat this word forever, poem, poem, poem. And so the LLM started outputting the word poem, and after some tens of outputs, it stopped, and then it output some sensitive user information. So it outputs some name, some email, some fax number, some phone number, and so on. And then you could check that this is not a hallucinated piece of information. You can go online and look for that person, and it's a real user who exists on the internet, and the information happens to be scraped on the web as part of training the LLM. So what this paper showed is that you could do this at scale. So you could show that for a careful prompt, you can get an off-the-shelf production LLM to output some verbatim information that is contained in the training data set. And this verbatim information can contain some sensitive user identifiers in it. So this is one privacy concerns. And as we include more and more user-sensitive data in the training data set, this problem will become even bigger. So the second privacy concern that I will be mentioning is related to LLM-based agents. So you can imagine a situation where we have an LLM-based agent that has access to personal information from the user, like the phone number or the list of medications of the user. And this LLM-based agent is supposed to take actions on the user's behalf. So for example, it's supposed to interact with some third parties, and depending on the context, exchange some information with the third party, including the user information. So one concrete example is if the third party is a restaurant and the user asks the LLM to book a table at the restaurant. So in this case, it's totally fine if the LLM shares the phone number of the user, but it's not okay if the LLM shares some medical information from the user. And there have been recent work showing that you can do some context hijacking attacks where the third party can get the LLM to share some information that's not acceptable depending on the context. So this is the second privacy consideration that I'll be mentioning. So in a nutshell, yeah, there will be the first one, which is a training side privacy risk, and the second one, which was an inference side privacy risk. And I'll be mentioning some mitigations that have been deployed and that are being researched in the space. So the first mitigation is to use regular expression-based sensitive information detection. So you can create a regular expression for every type of sensitive information. So you can have a regular expression for phone numbers, for addresses, for social security numbers, and so on. And in fact, these tools are available through many cloud providers, and they can be easily deployed at scale. While they are effective at detecting some very structured type of sensitive information, they fall short in a few ways. So one example is taken from this real user query in the chatbot arena dataset. So if you look at this query, there is no clearly, sensitive information in it. There is no name, no address, no phone number, nothing that clearly identifies the user. So if you run it through any of these regular expression-based tools, it will be a no-op, essentially. There will be nothing that is flagged, nothing that is detected or redacted. But if you zoom in on this prompt, and if you look at the information that I highlighted in red, it turns out you can stitch together this information and uniquely re-identify the user. So if you go to LinkedIn and look for a product lifecycle manager working in a Swiss company and who is pursuing an executive MBA, there is a unique person who meets this criteria, so you can uniquely re-identify the person. And in this case, if you trained your LLM on such a query, and if the LLM is outputting verbatim information, then it would be clearly a privacy violation. So this is one example where the regular expression-based tools fall short, but it's not the only one. They are also known to over-redact in some cases. So if you have a famous person or an address for a public landmark, the regular expression-based methods will flag it, even though it's not really a privacy violation. So now a second mitigation that is more powerful than the previous one is to use differential privacy. So differential privacy is a rigorous mathematical notion of privacy that applies to randomized algorithms in general and to machine learning models in particular. So to understand differential privacy, you can imagine a setting where you have two databases that differ on the contributions of one user. So on this slide, on the left side, I have a data set from user 1 up to user n. On the right side, I have a data set from the same users plus user A. So the only difference between the two data sets is the contributions of a single user. And differential privacy says that the output of the training procedure on these two data sets has to be approximately the same or indistinguishably the same. And if you have that type of guarantee, then you can show that input reconstruction attacks of the form that I mentioned on the first slide are no longer possible because the model is supposed to be the same whether user A is in the training data set or isn't in the training data set. So that translates into a very strong privacy protection in practice, and it rules out many privacy attacks. So it can be defined mathematically. So you can define it in terms of two parameters, epsilon and delta, that quantify the strength of the privacy protection. The smaller epsilon and delta are, the more private the training procedure is. And formally, you can have a notion of neighboring data sets which differ on the contributions of one user. And you have this training procedure M that takes an input data set X and returns a model. And you say that the probability that you output any specific model weights are roughly the same whether the input of user A is in the data set or isn't in the data set. So differential privacy has had many useful properties that made it quite popular. So if you go to any machine learning conference like NeurIPS or ICML or ICLR, and you look for a talk on privacy preserving ML, with high probability it will be a talk about differential privacy. And the reason why it's become so popular is because it has a bunch of useful mathematical properties. So first, it is closed under post-processing, which means that if you have a model that satisfies differential privacy, you can do whatever you want on this model, and it still satisfies differential privacy. It satisfies composition properties, which means that if you run multiple differentially private procedures on the same data set, the outcome is still quantifiably differentially private. it has a group privacy property, which means that if you protect the privacy of individuals, you can translate it into protections of privacy of small groups of individuals. And the protection degrades smoothly depending on the group size. And it can also be ensured via a simple noise addition mechanism that I will come back to later in the presentation. Moreover, it satisfies privacy amplification by subsampling, which means that if you take a differentially private procedure and you run it on a small sample from the data set, if you don't reveal to the adversary what is the small sample, then you get a strong amplification of the privacy guarantees through subsampling. And finally, it protects against input reconstruction attacks that I mentioned earlier. So it's overall considered a very strong notion of privacy. And one thing to mention is that although the focus of this talk is on generative models, it's been applied beyond machine learning. So one of the most publicized deployments of differential privacy was in the US Census in 2020. And it was a big release of a lot of user-sensitive data, and it was protected through differential privacy. So let me now quickly give you a flavor of how you can build a differentially private training procedure. So first, let me recall how usual training happens. So this is the typical mini-batch stochastic gradient descent that is used to train machine learning models. So typically, you start from some weight parameter W0, which is initialized somehow at random. Then for a number of iterations, you sample a batch of examples. You compute the gradient of the loss function with respect to every batch. You average the gradient, and you multiply them by some learning rate and update the weights of the model. And you repeat that over and over. So now to make this procedure differentially private, there are two ingredients that are used. The first one is to add some Gaussian noise in the training process. So for every batch of gradients, after you compute the average gradient, you can add noise sampled from a Gaussian distribution with zero mean and standard deviation sigma. And here sigma will be calibrated based on the privacy parameters and the privacy protection that you seek to enforce. That alone is not sufficient to ensure differential privacy because the sensitivity of a training example can still be unbounded. The reason is that in neural networks, we don't have any control on the gradients. So if you add or remove one example to the training data set, the gradient can be unboundedly large, which leads us to the second ingredient, which is to clip every per example gradient so that it has a bounded norm. So putting these two ingredients together, clipping and noise injection, you can get a procedure which is widely used in the field. It's called differentially private stochastic gradient descent, or DPSGD. And the privacy is analyzed by using the properties of DP that I mentioned in the previous slide. Specifically, you can use composition, post-processing, privacy amplification by subsampling, and get a provable bound on the privacy of this procedure. So the benefits of DPSGD is that it's a very generic recipe. It doesn't depend on the architecture or the activation. It also is domain agnostic, so you can use it for text, for image, for video, for speech. So quite general in that respect. There are also open source libraries and PyTorch and JAX, TensorFlow that allow you to train models with differentially private SGD. The downside is that it still incurs some utility drop, and it incurs some increase in the runtime. So those are the downsides. And there is a very active research effort and large body of work trying to improve DPSGD on the algorithm side, on the privacy accounting side, and so on. And many variants of DPSGD have been deployed in practice in some production use cases. So let me now mention one specific use of DPSGD in the context of LLMs. And specifically, this is in the fine-tuning stage. So typically, in fine-tuning, we're taking some off-the-shelf pre-trained LLM, and we have some smaller sensitive data set, and we would like to fine-tune this LLM on this small sensitive data set. And typically, you can apply DPSGD in the fine-tuning stage, and what you get out of it is a model that has a DP guarantee with respect to the sensitive data set that is used in fine-tuning. And this recipe has been applied in many scenarios, and it typically has a small gap with respect to non-private fine-tuning on the sensitive data set. And you can apply it both in terms of full fine-tuning, where you fine-tune every model parameter, or you can apply it with something like LoRa or some low-weight approximation without fine-tuning all the parameters of the model. Once you have a DP fine-tuned model, you can use it to generate synthetic data. And you can do that by just sampling or querying the LLM. And differentially private synthetic data is in a way the holy grail of privacy-preserving machine learning, because once you have generated synthetic data with some strong privacy guarantees, you can use it to train as many models as you want, and you can do it, use it to slice and dice the data in arbitrary ways without compromising the privacy of the users. So it's a very desirable primitive to have. And DP fine-tuning is one way of generating DP synthetic data. But it's not the only way. And there are other methods based on evolutionary algorithms. One of them is private evolution, which can also be used to generate differentially private synthetic data. And those don't entail training using DPSGD. So typically, they would start with some queries to some API, and then they would select from these queries the answers that are closest to the private data set. And this selection has to be done with some differential privacy guarantees, and then they bootstrap this process and iterate it over and over. So they query the API for some similar examples, then they select the one that are the most similar to the sensitive examples, and they keep repeating this process. So the advantage of this evolutionary algorithm is that it only needs API access to the foundation model, whereas fine-tuning needs access to the weights of the pre-trained model. So beyond synthetic data and fine-tuning, there are also active efforts to apply differential privacy to the pre-training phase. And in pre-training, there have been a few papers that highlighted the privacy risks that are related to a lot of personal information being present on the web somewhere. And this is typically picked up by foundation models, which are trained on all of the data that's available on the internet. And one way to ensure that the pre-trained LLM doesn't output some sensitive information is to train it with differential privacy. But this is still a frontier question in the field. So we've managed to train some smaller LLMs with DP, so roughly around 1 billion parameters. But still the field hasn't managed to train models with tens of billions or hundreds of billions of parameters in the pre-training phase with DPSGD. And in fact, only a few weeks ago, we put out the first scaling law for differentially private pre-training of language models. Whereas without privacy, scaling laws have been known for several years now. So this is still a very active area of research. So let me now discuss the last mitigation when it comes to training side privacy attacks. And this is about memorization tests. So there are situations where you may not be happy with the regular expression-based ways of detecting sensitive information, and you may not be able to apply differential privacy because of the cost overhead or the drop in utility. And one additional tool in the toolkit in this case is to apply some memorization tests to the generative model. And there is a sizable body of work on designing better and more accurate memorization tests. But roughly, the recipe is something like the following. You can insert some out-of-distribution canaries in the training corpus. So for example, you can go and add a sequence to the training data set that says the social security number of Alice is like this random value. You can then train the model, and you can measure the extent to which this random sequence was memorized by the model. So to do that, you can prompt the model after training it and ask, okay, what is the social security number of Alice? And if it outputs this random number that you injected in the training corpus, then this is an indication that this model is very susceptible to memorization. So these types of memorization tests have been productionized and scaled, and they can be used in many production settings. One observation here that links two of the previous mitigations is that DP, by definition, it prevents memorization when the privacy parameters are stringent enough. But empirically, what people have observed is that even if you train with DP with very loose privacy parameters, this is nevertheless an effective protection against memorization. So it's an empirical observation in the field. Okay, so let me now finally talk about some mitigations against the sharing of sensitive information by LLM-based agents. So recall that in this setting, we have an LLM agent that is acting on behalf of the user, interacting with some third parties, and the LLM-based agent is supposed to decide what information is safe to share with a third party, depending on the context. And here, the main tool that has been used is something called contextual integrity. So this has roots in the social science field, and it views privacy as the appropriate flow of information within specific contexts. So this is in contrast, with a binary view of privacy in terms of private versus public data sets and allowing anything to be done on public data sets and nothing to be done on private data sets. By contrast, contextual integrity posits that privacy has to be seen depending on the specific context. So they identify a bunch of parameters like what is the subject, who's the sender, who's the recipient, what is the information type, what is the transmission principle. And depending on all of these parameters, they deem some flow of information to be safe and some other flows of information to be inappropriate. And so this contextual integrity framework has been around for 2 decades, but it has seen revival of interest with LLMs. So in the last couple of years, there have been attempts to essentially teach LLMs the framework of contextual integrity, so that when you have an LLM-based agent that has to make a decision in the wild about whether some piece of personal information is safe to share with a third party, it can go back to these principles and figure out if the information flow is appropriate or not. So specifically, there is an active body of work that tries to assess the ability of LLMs to reason about what information is appropriate to share in different contexts. There are efforts to design contextual integrity-based systems to protect user information for different tasks. So there have been some papers around question answering, some papers around web form filling, and so on. And lastly, a few months ago, there has been a contextual integrity benchmark that has been proposed that contains synthetic evaluations for AI assistants when it comes to protecting sensitive information. So very active area of research. So let me now conclude with some open research questions in the field. The first one is whether we can design a system based on LLMs and that can detect sensitive information. So remember that the state of the art right now for detecting sensitive information is based on these regular expressions, which are very cheap to run, but they are very limited. And one can imagine a system based on LLMs that matches human accuracy. Like it matches the accuracy of the best human raters at detecting sensitive information, or it even surpasses the best human raters. And you could set the bar to be quite high in terms of matching the human performance, even when the human has access to something like Google search or LinkedIn or a lot of the public data that's available. And you would like to ensure that even when you have access to this public data, you cannot re-identify the user. So you would like the LLM to do that. So one angle here that is challenging is that these tools have to be run on a massive scale. So LLM inference is much more expensive than regular expression evaluation. So a bonus kind of aspect is to get such a system with a low inference cost so that it can be deployed at scale. The other research question here is to get differential private training to be scalable enough so that we can apply it at the pre-training phase and make it kind of a standard in all pre-training of generative models. As I mentioned before, we're still right now only able to train at around 1 billion parameters. So there is still a lot of work to be done to get it to train much larger models with little utility drop. And finally, the last direction is to find scalable and principled ways to operationalize contextual integrity for contextual agents for the long tail of tasks that users perform on the internet. Yeah, so this is everything I had. I'm happy to take any questions. Yeah. Okay, we can start here. I think maybe.
Okay. I can go first. If that's okay.
Who's speaking? Oh, okay.
Here. Yeah. So thank you for the lecture, by the way. I just wanted to ask a couple of questions. One, have you tried this technique basically builds an LLM that is promoting more privacy, right? Like it's preventing maybe the sensitive information. But have you tried to measure it against like building the regular LLM with a proper prompting, which is, I would say, a lot easier? And my second question, actually, does that work for other types of LLM's privacies? Or for example, does it work for images? Like if there is a password, like a snippet of a password and username, or it can be actually in speech as well, like if someone was telling their like their password and other, actually the examples can go and go.
Yeah, both are great questions. So regarding the first one, prompting can definitely, go some way in mitigating this problem. But if you think about an example such as the one I had earlier in the presentation, so this LinkedIn example, it's very hard even if you prompt carefully, an LLM, it's very hard to get it to flag this as being a sensitive information, because you will need it to kind of check maybe LinkedIn to see if this is a real person or not. So it feels like prompting will be useful, but it will not solve the entire problem. And regarding the second question about what methods could be applied to other modalities beyond text, like images or speech, that's a great question. And to the best of my knowledge, the state of the art is something like first converting them to text and then applying the tools that are available for, text-based sensitive information detection.
Can I go first?
Who's speaking?
Yeah.
Oh, yeah.
Thank you, Dr. Badih, for this informative talk. I have two questions. The first one is regarding differential privacy. As per my understanding, differential privacy was first introduced by dogs for retrieving queries from tabular data, where it made perfect sense because it guaranteed privacy. And using it beyond that scope, for instance, for textual data or visual data, we are losing that guarantee that was promised in the first place. And the trade-off is always going to be there, since we are relying on noise and the value of epsilon that's being used. So do you think it is still applicable to other data beyond tabular data, such as textual data or visual data? Because not only are we losing the guarantee that was promised, but we are also losing utility, as you mentioned. So is there any scope for using differential privacy in this case or not?
Yeah, good question. So regarding the type of data, so let me just find that slide. Yeah, so this is the slide about differential privacy. So if you see here, the algorithm block is just a black box. It can be, you know, some algorithm that is used in the tabular data setting. It could be some algorithm that has some image processing components, some like text processing component. It's unrestricted, and the definition of differential privacy that I have on this slide is totally oblivious to what the algorithm does or what the domain is. So I wouldn't say that, you know, differential privacy is specific to a certain modality. You have to be careful when it comes to text and images to precisely pinpoint what is being protected. And in the case of this talk, it's the model that is being trained on the images or the text. The output weights of the model are the ones that satisfy differential privacy. Regarding your second question about the utility drop, that's a challenge in the field, and a lot of the work that I alluded to, you know, in like top machine learning conferences, it's exactly about closing the gap in utility between private training and non-private training. So
okay, lastly, you did not mention unlearning techniques. Is there any scope for unlearning techniques in LLMs or not? Thank you.
Yeah. Great question. We've had some work on unlearning as well, and it's also a frontier research challenge. So there, you would like, you know, to take out some training example from a model and to do it in an efficient way. It's related to privacy, and that if you have a model that is trained with differential privacy, it's easy to unlearn, you know, one or a few examples from it. But it's also challenging in practice, and I am not aware of any, you know, widespread deployments of unlearning techniques in practice. But very interesting research questions. Yeah, but it's a bit of a chicken and egg problem because you don't know what is the sensitive data you want to unlearn in the first place.
Thank you for the talk.
Mm-hmm.
I have 3 questions. So the first one is regarding the clipping constant. What I usually see in the literature, it's kind of empirically put there.
Yes.
And is there like a way more formal to decide what we put as a clipping constant? So this is the first question. The second one is about Bayesian inference. So actually there is some ongoing work that kind of guarantee differential privacy for free just by doing Bayesian inference via sampling, MCMC. And but this is not yet the case for variational inference. So do you have any idea on some research on that field? The third question is, so as far as I know, DP could be a bit rigid, let's say, as it considers worst case scenarios. Could we relax it more? Yeah, I think that's it.
Yeah, so for the first question about the clipping constant, yes, in the most, you know, vanilla deployments of DP-SGD, it is treated as an additional hyperparameter. And it's a bit tricky because if you're doing hyperparameter tuning with privacy, you have to worry about the privacy budget that's used for choosing the value of C and so on. That said, I'm aware of some, you know, prior papers that set C in an automated way. So roughly what do they do is throughout the training, they keep track of the distribution of norms of the gradient, and then they set C depending on some quantile of that distribution. So they have to estimate this quantile with some privacy budget, but it is doable and it has been done.
Can I have like a reference for that, please?
Yeah, I can send you some
thanks.
reference. Yeah, regarding the second question, I'm not aware of any, you know, work on the variational inference side. For the third question about DP being rigid, yeah, that is true in that it's a very worst case guarantee. So it's like a very strong guarantee of privacy if you think about it. And in many cases, you know, a realistic adversary could be weaker than what DP protects against. One can view the memorization tests I mentioned in the presentation as being kind of a fallback if you deem DP to be very strong. And there are works on coming up with milder notions of privacy, but I don't think any of them has been as universally accepted as differential privacy.
Yeah, but that's a problem of like the academia, let's say, environment, or the new ideas, let's say. What do you think? Is it like because the academia is kind of rigid of accepting a new idea, or it's because of the new ideas themselves?
I feel in this case it's more the new ideas themselves. Okay. Yeah, like DP has really picked up because of all of these nice properties that it had. Many attempts at defining, weaker forms of privacy are much easier to attack. So it's harder for them to, stand the test of time.
Okay, thank you.
Thank you, Badih. Yeah, here. Yeah, thank you, Dr. Badih, for this amazing talk. I have 3 questions or 2. The first one is about the intuition of DP. So the intuition of DP goes by adding random or adding noise during training. But I have a question like, isn't it more efficient or makes more sense that we add targeted noise to training samples that have sensitive information? Or so we go like a hybrid approach between categorizing or classifying sensitive information and adding noise instead of adding noise in general. And this brings me to my second question regarding memorization. So you said that DP helps avoid memorization, but it's also the memorization problems of LLMs. Sometimes we need memorization. So if we are asking about a general information or a fact, we need the LLM to have known the fact before and memorize it and tell it to us. And the third question is about I'm wanting to know how much is the scale of difference between pre-training and a foundational model or an LLM with DP versus without DP. So what difference are we talking about in terms of computational power and time? Thank you.
Okay, great questions. Yeah, so for the first 2 questions, they are about adding, targeted noise. If you have some knowledge of which piece of information may be sensitive. So there is a sizable body of work on this topic. So usually it is framed as public-private training. So you have 2 parts in the training data set. Some sequences or tokens are public and you're absolutely sure that they don't contain sensitive information. And the other sequences are private. And in this case, yes, you can do much better than generic DP-SGD. You can just target the noise towards the sensitive part of the data set. So yeah, and I can send you some references about that. The second question, what was it?
Memorization.
Oh, yeah. About memorizing sensitive information. So it's a bit similar in that if you know that in the pre-training corpus, you have Wikipedia or like some part that contains maybe no sensitive user information and you're totally happy if the LLM memorized facts from Wikipedia, then you don't need to turn on DP for that part of the training corpus. But when you inject some user information, then you turn on DP only for that part. And the third question?
It's about the
the blow up, yeah. So I can share with you the scaling law papers that we have. It's hard to summarize it really in one number because it depends on a bunch of parameters. But you can think of it as, maybe between a factor of 5 and a factor of 10.
Okay.
Blow up. Yeah.
May I just ask a quick question? You said we can detect the person from the LinkedIn, but as the person publicly shares the data, how can we decide this is a private thing or not? If this was just public data, why don't we consider this as not a problem?
Yeah. So here, the privacy risk is that this specific prompt was not shared publicly. So in this specific example, you guys might have used Chatbot Arena, where users can just go query it with some private prompts. And their expectation is perhaps that this remains a private information. So in this case, this person was typing this information in Chatbot Arena. Later on, people who released these data sets from Chatbot Arena, they deemed this as being safe because, looking at it, there is no sensitive information inside this data. But the point is that you can now join it to a specific person on LinkedIn. And if you go back to this this query, it might contain something about what the person is up to, like maybe they are applying to new jobs or new opportunities. So in that sense, it's a privacy violation.
You mean like the prompt is private?
Exactly.
Okay, okay. So the information is not a problem, but like connecting.
Yeah, yeah.
Okay, thank you so much.
Cool. Oh, there is one here.
Thank you for the talk. I want to ask a question about DP. So you mentioned that we're adding noise in the gradients, and from a naive understanding, I suspect that it will reduce the model performance, right? Like there will be some effect in the model performance. So I want to understand like how much degradation do we experience after like doing this DP training?
Yeah, it's highly dependent on the setting and the use case. Yeah, it's hard to give a specific number. It also depends on the model size, the training data set, and how much compute you have. The scaling law papers that I have does a systematic study for pre-training, so I can point you to that, but it's hard to summarize it in one number because it's very dependent on the setting.
Okay, thank you.